set up yesterday.
I would try. Am I after you? So, you are. Malore. He's last. So he's last. So, okay. So there we go. I was trying to figure out. I was like, am I in 2 or 3? I can't figure it out.
Oh man, never in my life have I been, well, not since I've been married. First for everything.
He's kind of end up in the middle of the mix, so usually
Yeah.
I say,
Well,
So I think we're going to get started here in just a minute. So if you guys can find your seats. No, I know. I'm at the crowd. Do you want it in there? I should not take this out.
All right. Well, good evening, everybody. My name is Jomo Stewart. I'm the president and CEO of the Fairbanks Economic Development Corporation, and Gwen told me we're starting now. So, welcome, everyone. So a couple of things, if I may, just right at the very top. Let's do our safety minute. We are here in the Fairbanks Pipeline Training Center. You'll notice that there are a couple of exits just over, I guess, on your left. Okay. Also, you saw the exits when you walked in the door. So just know that those are around, and just be aware. As far as bathrooms are concerned, if you walk out into the foyer, they're on the right, centered in the foyer. There are the bathrooms, ladies on the right, gentlemen on the left, in case anyone needs those. And of course, there's coffee and tea there in the back if anyone needs any refreshments. So I would like to give a special thanks right at the very top, of course, to UAF, to ACEP, the Alaska Center for Energy and Power, but a very special thanks right at the top to Mr. Jim Sampson and the Pipeline Training Center for allowing us to have this function here. The Fairbanks Pipeline Training Center is a remarkable resource, and Mr. Sampson helped get it established here in our community, a place where Alaskans could learn the pipeline industry and that work, energy. So, again, I'm Jomo Stewart, Fairbanks Economic Development Corporation. I get the chance to introduce Ms. Gwen Holdmann. Ms. Gwen Holdmann is now the Associate Vice Chancellor for Research up at UAF, formerly the top at the Alaska, and helped establish the Alaska Center for Energy and Power with the dream of having Fairbanks, Alaska be the center of energy research and innovation in the state of Alaska, but also around the world. And has done a remarkable job in that capacity, helping with this subject at hand, helping Alaskans get a better understanding about the energy options that might be available to us, but also to help vet them to see how and make sure that they would be appropriate for our communities in our environment. Because in the end, it's all about people. So one last little word about me. So again, I'm the president of your Economic Development Corporation. I've been working there. I've had the pleasure, the honor and pleasure of serving you in that capacity for over 15 years. I just recently got elevated to president and CEO, but I worked there as staff forever and a day. I have spent a lifetime trying to figure out what might help our economy. And the single biggest thing that I've been able to identify over that long span is to reduce and stabilize the cost of energy. When you live in one of the coldest, darkest major metropolitan centers on the face of the planet, energy is a big, big deal. Its availability, its safety, its reliability, but critically its cost, because it can either act as a floor that we can build on for a more prosperous future, or it can be a sea anchor that weighs us down and holds us back. And for too long and in too many places, that is what energy has been, a sea anchor that holds us down and holds us back. I don't know if nuclear power is the solution to the energy challenges that face us and our communities, but I do believe, and certainly from the research that I've done and from the information that I've been able to glean, I do believe it will have a role to play. It can have a beneficial role to play. For our part at FEDC, we're not here to tell you what to do. We're not here to tell you what to think. But what we do try to do is get the best information possible into the hands of the citizenry so that you can make informed decisions for yourselves, your households, your businesses, your community, and our state. And so I hope that you'll accept our offer of information. There on the stand, there is a sign-up sheet for one of the enterprises we offer there at FEDC. So it's euphemistically called the Tuesday Morning Task Force. What it is the Energy for All Alaska Task Force. It meets every Tuesday from 8 to 9 a.m. And again, energy is the major subject where we try to get people like the speakers that you're going to be hearing from over the course of the next couple of hours to come in, give presentations regarding their ideas, their innovations, but also to answer your questions regarding those technologies. Fair enough? So if you'd like to be part of the group, please do feel free to sign up. We're over 200 strong now, and we'd love to have you. Without further ado, please let me introduce Ms. Gwen Holdmann.
Thank you, Jomo. I really appreciate Jomo and the Fairbanks Economic Development Corporation co-hosting this event tonight. This is the second in what I'm hoping will be a series of community town halls on the topic of nuclear energy, small nuclear reactors, and the potential that has for our community and for our state. I'd like to really echo Jomo's comments about the idea of using these sorts of forums as a way to share information publicly and make sure that Alaskans are able to make informed decisions based on the best science that we have available and the information that we can share with you. And I'm really pleased today because we have an opportunity. There was a pre-proposal conference and site visit today or yesterday at Eielson Air Force Base for vendors that are interested in potentially bidding on the planned Eielson Air Force Base microreactor project. And I thought it was an excellent opportunity for all of you to hear from some of the top companies in the industry today that may have an interest in this market in Alaska and learn a little bit about the technology that they're specifically proposing and advanced reactors more generally. I'd really like to thank the team at ASAP for doing a really fantastic job. Amanda, Jeff, Colleen, thank you so much for all of the work that you've been doing in getting information out to the public to make sure that we have a really diverse crowd here. We really want all perspectives to be brought to the table. We want to hear and be able to address any questions and concerns you have. And so with that being said, the way we're going to organize this tonight is I've asked each of the 5 vendors that are represented here today, so that's NuScale, BWXT, Westinghouse, Oklo, and USNC, Ultrasafe Nuclear Corporation, to come up and give a 5 to 8 minute introductory presentation about their technology. I'm having them do that in alphabetical order by last name. And then in terms of Q&A, I'm just curious, how many of you were at the town hall that we hosted a couple of weeks ago? Can you just raise your hand if you were there? Fantastic. Okay, so about half of you or so. And I should also acknowledge that we are live streaming this event, and so we have people joining us from all over the state. And thank you, Jeff, for monitoring that. We'll also be taking questions from the online audience as well. We've got cards, Jomo, Vanna White over there. So this time around, the last time, we got a lot of questions, and it was a little difficult to manage. And so I'd actually like to ask you to write your questions down so we can kind of curate them and make sure that we're sort of getting to them. And so I'll go ahead and sort of moderate the Q&A portion of this. So we'll give you guys lots of opportunities, like, you know, raise your hands right now. If you think you're going to have a question and you want a card, raise your hand now and we'll get one to you. Otherwise, we'll do that in between some of the vendor presentations as well if one of them comes up. And let's see, I also wanted to thank Alaska Universal Productions for helping with the audiovisual, the AV stuff here, because I don't know who was at the library one, but we've had a few issues there, and so we've decided to just hire the experts to take care of that part for us, and I think that's taken a lot of the pressure off of the ASAP team, so thanks a lot. And so before we start, because we just did have this Eielson site visit that the Air Force hosted, we also have some representatives from the Nuclear Regulatory Commission here, Ken Irvin and Ben Beasley, is that right? And so I just wanted to give them just a minute to talk a little bit about the licensing process, just really informally, and just introduce themselves from the Nuclear Regulatory Commission, just so that you're aware of that side of the process.
Thanks, Gwen, and good evening, everyone. My name is Ken Irwin. I'm from the United States Nuclear Regulatory Commission. We are a small independent federal agency responsible for licensing all the commercial use of nuclear material in the United States. You can sort of think of, if you've heard of the SEC or the FAA, very similar role except for commercial use of nuclear material. We would be responsible for licensing any commercial power plant in Alaska. And we were up here at the request of the Air Force to support their meeting, just to talk about who we are and answer any possible questions there. Our mission is to protect the public health and safety, and we have a very involved licensing and outreach program for any future license application that would be done here. Ben and I will be around the whole meeting, so you can submit, if you have questions for us, you can submit them to Gwen, or you can pull one of us aside and talk to us. We try to be very approachable. And we also have a lot of information at our website, which is just www.nrc.gov. So I hope you have a productive meeting.
Thanks a lot, Ken. And I'd also just like to acknowledge Allison Natcher. If you could just stand up and wave to everybody. Allison is our state liaison to the NRC. She's with the Department of Environmental Conservation. So she's been a really fantastic ally and working a lot on these issues at the state level. And then also wanted to acknowledge Jeremy Casper, who is now the interim director of the Alaska Center for Energy and Power. So he's made it possible for me to spend more time on some of these strategic initiatives while he's holding down the fort at the Alaska Center for Energy and Power. And so, as I mentioned, I've asked the vendors to come up in alphabetical order. And Lisa, I don't know if you got the short end of the stick or the long end of the stick, but Lisa Morgan with NuScale is going to go ahead and kick us off here. Do you want to hold it, or do you want to?
Yeah, I'll
Okay.
hold it. And this is the clicker right here, right?
Yeah.
It's the first time that I've actually been first with my last name starting with M, but. Oh. Should we switch, or should we? That's okay. Okay. All right. Good evening, everyone. My name is Lisa Morgan. I'm a systems engineer with the Office of Technology for NuScale Power. So today we're going to talk about, we actually have a couple of different reactors that we're going to talk about from NuScale that we think could be applicable in markets here in Alaska. Am I pushing? Okay. Well, preview. Okay. NuScale's core technology we refer to as the NuScale Power Module. This is not a microreactor. This is actually classified as a small modular reactor. As you can see, the reactor itself is shown on the left side. The difference between this and traditional nuclear reactors is nearly all of it is fabricated in the factory. So it's basically trucked in big chunks instead of having to be fully built on the site of the reactor. It also has the steam supply, so the nuclear reaction is what creates the heat, but then there's steam that's generated. It's all happening within the containment vessel versus having to go through different outside systems to generate steam. So that steam supply is all within the containment of the module. The simpler design here has eliminated the reactor coolant pumps, so there's actually natural circulation that's used instead of having to pump the fluids around to cool the system. Because of the simpler design, we were able to make a very strong safety case to the NRC. Our design was the first to be approved by the NRC. That's considered a small modular reactor. The idea behind it being modular is you can create a plant where you add modular reactors as you need them. One single module produces 77 megawatts of electrical power. We have basically 3 different plant configurations in our business model right now. We have a 4-module, a 6-module, and up to a 12-module plant. So a 12-module plant would give you 924 megawatts of electrical power, so that's pretty good supply. The design life is 60 years. Our fuel supply, we're not using novel fuels. We're using the same fuels that have been used in historical reactors. And we consider the design to be walkaway safe, which means if there were to be some safety condition that required evacuation, everybody could leave. There wouldn't need to be external sources of water brought in. There wouldn't need to be operator interaction to keep the system in a safe mode. It would be prevented from melting down. And the emergency planning zone, which is the area around the site that would need to be mitigated in a case of emergency, we believe is going to be within the site of the plant itself. So usually I have a slide coming up that shows a typical emergency planning zone versus the footprint of our emergency planning zone. Next slide. I'm in control. Maybe? Oh, okay. Sorry. Okay, so I spoke to this already, but we think that the Alaska market could benefit from a 4-module plant. You would get 308 megawatts of power output. It has the same, all of the plants, regardless of the number of modules, have a similar safety strategy, similar type of footprint. You're just changing the size of your reactor building, the size of your peripherals to generate power. We believe the applications for a plant like this could be small grids, which we know you have many of in Alaska now, island nations, remote off-grid communities, possibly industrial or government facilities. This is definitely bigger than what they're asking for the Eielson pilot project, but also as coal power replacements. So if I go to the next slide, what am I pointing at? Okay. We actually think that these power plants can be built to replace retiring coal plants. So the numbers up here are for a 12-module Voyager plant. So it would yield 1,200 construction jobs for 3 years, operations jobs, and our operating life is 60 years for a plant, as well as other indirect jobs. It would preserve the local tax base. So obviously the numbers would be scaled down for a 4-module plant, but it's not necessarily a linear scale, the construction jobs especially. We believe that these can be sited at retiring coal plants or other existing fossil fuel plants, and that the workforce could be retrained. So we've actually done some analysis to kind of map the jobs at current fossil fuel plants to what the equivalent jobs would be with retraining at the new scale power plants. This is my last SMR slide here. So we talk a lot about our inherently safe design and it being a new standard for the industry. So I just want to point out here that the things shown on the left talking about the different generations of reactors, all of those reactors have a proven history of safety. All reactors are operating safely currently. The difference between our reactor is that ours is walkaway safe. So if there were to be a problem, it could basically be in an unattended state for an unlimited amount of time, and there would need to be no interaction to keep that reactor safe and no hazard. So I mentioned earlier the emergency planning zone, so it's kind of hard to see on the projector, but there's like a big kind of shaded circle that shows a typical large-scale nuclear EPZ, which is a 10-mile radius, and then you can see that tiny little dot in the middle is the NuScale EPZ. So really it's, we can site these closer to population centers than typical nuclear reactors because they're smaller and they are inherently safe. Just on the right side, just some additional capabilities that you're getting from a small modular reactor that it doesn't exist for a lot of current nuclear facilities. We can operate without connection to the grid. We can provide basically startup power back to the grid in the event of a loss of power. The power is highly reliable, and flexible siting options means that we only need to, it can operate off-grid or at the endpoint of a grid. So that's all I have to say about our SMR. I talked about that because that is NuScale's kind of bread and butter right now. But we are also developing a microreactor. So that's what the rest of the presentations I think are going to focus on. We're doing market analysis. We identified these different markets. So we're very interested in working with universities to deploy new research reactors to further the study of nuclear engineering. We believe microreactors are appropriately sized for mining operations. Also, our design can be used for either space or terrestrial power. Remote off-grid communities, again, microgrids, replacing some existing microgrids or augmenting existing microgrids. Permanent military installations, this is a stationary reactor, it's not a mobile reactor. And then in the event of a disaster where the power grid is severely compromised, being able to stand it up quickly and help recover that power grid is another application for the microreactor. So the thing about the microreactor is it has no moving parts for power production. Everything is happening by natural circulation, similar to the SMR. So our conceptual design is really focused on a similar design for both space and power applications. It's small and compact, highly reliable, automated, and it can be stood up quickly. So very similar between the space power and the terrestrial power designs. We're using we're using liquid metal for both our fuel and our coolant. So that's something that has not been licensed before. So that's something that we're doing a lot of development testing, and we're gonna do early engagement with the NRC to make sure that we're working together on getting through licensing in a smooth way. Once the reaction occurs, we're using heat pipes to transfer the heat into our coolant moderator, and then transfer that to the power conversion system. We have different options for power conversion, either using thermal photovoltaic cells, or we can also incorporate an open air Brayton cycle for our largest model. So because of the lack of moving parts and the simplicity, we have inherent protection. We don't use fuel rods, so if we needed to shut down the reactor, there's no moving parts involved. We think this enables a cost-competitive, reliable design. And then as far as sizing goes, we are designing for 1 to 10 megawatts electric for terrestrial application, or 40 kilowatts to 1 megawatt for space applications. So that is all that I have. Sorry, I talk fast.
Yeah, no, that's great. Thank you. We're going to try to adjust the lights so that the lights are off in the front here so we can see the screen a little bit better. You are our guinea pig, Lisa, so we didn't want to start flashing the lights. I think that works better. So next up, Josh Parker with BWX Technologies.
Thank you, Gwen. Josh Parker, Director of Business Development with BWX Technologies, Inc., and their Advanced Reactors Division. So I'll give a little bit of background about BWX Technologies. Anybody U.S. Navy here? Anybody serve on a submarine or an aircraft carrier in their life? Thank you for your service. You are a direct user of BWXT's technologies. BWXT, our company history is with Naval Nuclear. We have 6,600 employees. We are based in Lynchburg, Virginia, so all the way on the other side of the country. We have 12 major manufacturing facilities that delivers those reactors for the Navy every year. We make 2 to 3 reactors. We also refuel research reactors in the United States as well as overseas for the high-performance research reactors, just as those that you would find at Oak Ridge National Lab or Idaho National Lab. We do 8 to 12 cores of those a year. We also serve the Canadian business as well. We have a footprint up there with the commercial nuclear and their CANDU fleet, and you can see over there some of the numbers that we provide, both the fuel and other operations for them. We also have an arm of our business that supports the national labs through management and operations as well as environmental cleanup. So that's a little bit about us and what we currently do today. We have a history. BWX Technologies may not be known, but actually Babcock & Wilcox is a fairly old name. We are the successor to that company. Came out of Stephen Wilcox in the water tube boiler. Those sometimes are still used in fossil industry today. We've got a long history in naval nuclear, first nuclear reactors as well in this country. We were both commercial and defense. We split that business back in the 90s. And then in 2015, we actually split the fossil side of the business off and focused on solely the nuclear side of the business. It allowed us to focus on new and novel technology. We targeted space applications and advanced reactors for terrestrial applications. We also got into medical isotopes and brought back the capability to make TRISO fuel, which is an encapsulated fuel product for the advanced reactor industry. So what does the Advanced Technologies Group do inside of BWXT? So we are looking at space nuclear, so nuclear thermal propulsion. Cuts the travel time to Mars in half. You reduce the human exposure to cosmic radiation, gets you there quicker, and provides for aborts. We're looking at lunar surface power, providing power for the moon for bases there, jumping off point for future technologies and exploration, nuclear electric propulsion as well for strategic initiatives. We have terrestrial reactors and specifically in the microreactor category, and I'll talk about the two of them. They're smaller than small in some cases. We also, as a manufacturing company, we say we're not going to design anything we can't build. So we invest in the advanced technologies, the advanced manufacturing techniques that are necessary to bring these reactors to market. So not only the fuel, but also the capabilities to weld vessels, stand up things, looking at additive manufacturing and the quality that's required to go into that and make it more cost effective. We also go into saving lives. We develop medical isotopes. We deploy those. We have a subsidiary that actually exists in Canada. The development of that technology, though, actually takes place in the Advanced Technologies arm. It's industrialized in Canada. We just submitted an FDA application for Moly-99 production, which is a medical isotope that's used for diagnostic imaging throughout the world, and will help expand the supply of that. So, I already mentioned we have space concepts and development. I'll talk a little bit here in just a minute. We actually are building a first-of-a-kind microreactor for the Department of Defense, and it's in the early stages of manufacturing. We're making procurement and buying parts today. We are in the small categories. We're 1 to 20 megawatts electric. I've got two designs I'll share with you. They are portable, they're scalable, and they're factory fabricated. So we have that history in our background of what we do. We're looking at electricity, heat, desalination, hydrogen production. Where does nuclear make sense and plug into make and enabling technologies? And we work with private and government support to enable this technology. So I mentioned the Department of Defense reactor. It's known as Project Pele. It's a 1 to 5 megawatt electric microreactor. It is a high temperature gas reactor. It is using the TRISO fuel, which I often call the everlasting Godstopper. So you've got a very center of uranium, and then it has 3 coatings on the outside to contain all the fission products inside of it. So imagine the head of a ballpoint pen, and that's the size of a TRISO particle there, and it holds all the fission products and radiological issues that you would have inside a reactor inside of that. This reactor is, like I said, being manufactured. We are procuring parts today, and it will be deployed at Idaho National Lab in 2024. It's going to be transportable within commercially available shipping containers. The DoD said, put it in a 20-foot Connex box. So we've got those that will be there. We've got an experienced and capable team that goes beyond BWXT in delivering all the technologies necessary to bring this to reality for the Department of Defense. We have a slightly larger reactor design. We're very creative with names. We call it Banner, which stands for BWXT Advanced Nuclear Reactor. I keep trying to convince them that we ought to get Bruce Banner and the Hulk to advertise, but we don't have that budget. So you may be familiar with the Department of Energy Advanced Reactor Demonstration Program. We're in the risk reduction category, which is a category 2. Risk reduction means that we're shooting for economic improvement of the reactor. So we're targeting a couple of technologies to bring this technology down to a cost-effective level, theoretically cutting the cost in half. It is also a high-temperature gas reactor, so some similarities with Project Pele above. It's 50 megawatts thermal, 17 megawatts electric, so quite a bit bigger than the other one. You can scale it. You can put multiple units on a site. It's got a high power density fuel. It's the TRISO fuel as well. It's got a 5-year refueling cycle. Inside of that reactor, there are 5 modules there that you need for a high temperature gas reactor to make this work. Every last one of them, as a requirement, has to fit on a commercially shippable truck. I don't need special transport. I can put it on there and get it to the location. We also required it on rail as well. That kind of set the size, and that's how you kind of get to 50 megawatts in the end. Once again, looking at passive safety, which means you walk away safe. You know, colleague here from NewScale did a good job of outlining that. So we got that in the technology there. Rapid modular installation, you slide these skids in, you install them. Refueling, we don't intend to ever open that core. It's as a cartridge. We take it in and out, so you don't have nuclear fuel shuffling or handling that you would have in larger nuclear power plants. We try to use what's known as high technology readiness level tech to do this and deploy. So you'll sometimes see us throw acronyms around, and I apologize for that, but that's what TRL means. So thank you for your time today. Looking forward to your questions here.
Thank you, Josh. If anyone has questions for Lisa or Josh, or thinks they're going to have a future question, or for the Nuclear Regulatory Commission, raise your hand and we'll get you a card. Just so want to give everyone that opportunity. We're going to go through all the speakers before we switch over to Q&A. And so next up is Emma Red. Whoa, are you up next? Yeah. All right. We're just doing it that way. Christian. No. Come on. I don't know. We can't. I guess I can't do alphabetical order. That was too complicated for me. So, Christian Rabahati from Ultra Safe Nuclear Corporation.
Hi. Well, thank you everybody for being here. What is the click? Yes. Oh. All right. Someone did it for me, I guess. Okay. Ultra safe nuclear technology. I have a little bit of an accent, so I'm originally from Italy. I've been here in the US since 2005, been in the national lab, and I think that at a certain point I thought the technology was ready to go out from the national lab, so I decided to join the industry. And I think that it is an exciting time, it's an exciting technology, and we are ready for prime time. And it's not really me, okay. Okay, so a couple of words about USNC, Ultra Safe Nuclear Corporation. So the company is about 250 and growing very fast. When I joined the company, it was about 150 people, probably, and every time I look to this slide, the numbers goes up by 50. It's pretty fast. We are, in a lot of locations worldwide. Our headquarters is in Seattle. I actually live in Idaho Falls. We have a small office there. And we have facilities actually in Salt Lake and in Oak Ridge, where we produce fuel. So our pilot facility for the production of the fuel has just started. And so what I want to say with this is that, next slide, yes. What makes special our technology is really the fuel. So in 2011, when there was the Fukushima accident, our CEO was asked to come up with a design for a fuel that was not susceptible to the type of accident. So we heard already about how nice is the TRISO fuel. So what we decided to do is actually make it even more safer. So the TRISO fuel that was explained with this coating that protect the release of radioactive material, actually we decided to embed it inside silicon carbide. Think about having this fuel and then put the most safe fuel so far created inside a material that actually is tank armor. It is used for tank armor. And it's a very complex process, but at the end of the day, what you get is a really solid block of silicon carbide with inside a TRISO. So this is what really allows us to have a concept of a reactor that we say that is walk away safe, also come back safe. So the concept is that the margin of safety of the reactor should be so large, should be so forgiving that even if no one hacks, the reactor not only is going to be safe for the surrounding, but it's going to preserve itself without being damaged. So operationally speaking, the reactor will not be damaged if it is left by operating by himself. So this is an important concept because not only we save we make the population safe, we also make the investment safe. So if, next slide, how do I do that? Okay, so our design is underground. It's about 5 to 10 megawatt electric, which is equivalent to 10 to 30 megawatt thermal. Think about it as being like, I would say between around 15 yards underground. And the reason why we like that configuration is because it is actually very difficult to access to the reactor. Even if you would like to damage the reactor is not really exposed. So that makes one level more of safety in terms of how we protect the reactor itself. We refer to this reactor as a battery more than a reactor. The reason why we think in that way, because in reality is an energy container. So that core that you see there contains about 3 billion kilowatt hours. And the time that is going to last really depends how fast you want to drain that energy. So you would operate the reactor, and if you operated a very high level of output, it's going to last less. If you operated slower, it's going to last longer. So I think really to this reactor like a slow burning candle. It takes a long time to run out of energy. And I say slow burning because the level of power of the reactor is always very low, which goes back to the concept of safety, because that says that the risk, which is proportional to the content of energy, to the power that is inside, is always very low because this is a very slow burning machine. And that helps with the concept that I just said before, that is a walk away safe and come back safe. Just having a feeling about what a plant may look like. It's about 200 yards by 100 yards, what you see there, 2 units. The reactor was actually conceived for this type of application in terms of remote and mining. So it is a waterless, so no resources are needed. It is a plant that is easy to deploy. It's about 6 months construction time, and also it really works very well with both variable renewable and with solar and wind. And with the fact that you may not need always 100% of the power. So this reactor will go up and down, and also will have a storage system that will store the heat. So depending, maybe in the night, maybe in a sunny day, you don't need a lot of energy, so you can actually store that energy in excess in a molten salt system and actually take it back later on when you really need it. We have actually 2 ongoing projects. One is in Canada. It is our first deployment, and it's going to be operational by 2026. I don't want, there is, the only information that I really want to transfer with this slide is the fact that our first operation is going to be 2026. We have a very strong team and a collaboration with a very large operator in Canada, which is Ontario Power. In terms of timeline, that allows us to say that in 2027 we will be commercial, and it will not be first of a kind, because actually this is going to be the first of a kind, and the next one is going to be the second of a kind, which is the University of Illinois. And I want also to draw your attention to the fact that the reactor at the University of Illinois is going to be built on the university campus. So we go back to the discussion and to point out that it will be possible to build these reactors close to the population. They are not a threat to the population. So the region that you need actually to the expectation, of course, is going to be the NRC to have the final word on this, but the expectation is that the zone of safety around the plant will not be extended outside the plant itself. So just to summarize, I think that the microreactors are becoming a reality. They are a CO2-free source of energy. They are very flexible and capable to work also in isolation, in microgrids, which is key. And the reason why they can do that is because the refueling is going to be once every 10, 20 years. They will be able to go up and down. They will be able to follow the demand of the local grid. Then the fact that these designs are conceived, especially this one is conceived for remote application, with a very low dependency on natural resources like water, also help the deployability in environments like Helizon or other region here in Alaska. And probably most of you knows that we are currently working also with Copper Valley, and we are doing some studies together to understand if it is, an option for them to use one of our reactors. I think that concludes my presentation.
Okay, Emma.
Thanks so much, Gwen. Thanks to everybody for being here. I appreciate that this many people turned out and are interested in engaging in a conversation about advanced nuclear in Alaska. My name is Emma Redfoot. I'm the siting lead for Oklo. My background, I grew up in Montana, and growing up there inspired me to go work on environmental issues, so I got a degree in environmental studies. I got really interested in energy while I was getting that degree and realized how important it is for people to have access to energy, as well as how important it is for that to be clean. So after school, I did a lot of research in energy and then decided to go back and get my master's in nuclear engineering. And you can see my email up there if you have more questions after this presentation. Okay, path to market. So Oklo, this gives some of the general bullet point accomplishments that Oklo's already met. Oklo is the first non-light water reactor to engage with the Nuclear Regulatory Commission, and we started that in 2016. Oklo obtained a site use permit from the Idaho National Laboratory site right outside of Idaho Falls, so that's where our first deployment's going to be. We got that in 2018. We were also awarded fuel for our first deployment in Idaho Falls, and that came from the experimental breeder reactor 2, which I'll be talking about a little bit more later on. And we also submitted a license application to build and operate our first plant. The first application we submitted was a pilot application in 2018. We worked with the Nuclear Regulatory Commission, got a lot of feedback, learned a lot from that, and that led to us submitting another application in 2020. That 2020 application, we got a lot of information from. Of course, we submitted the application March 11th, 2020, which is the day that the pandemic was declared a pandemic. And the plan that the NRC had laid out included a lot of, working together in person, and then all of a sudden things changed and we were doing a lot of virtual communication, as well as trying to license the first of a very new kind of reactor. So that was kicked back to us in January of this year. Since then, we've had a lot of good conversations with the NRC and continue to collaborate moving forward on licensing that reactor. So in terms of our timeline, our first commercial plant, the one I've been talking about in Idaho Falls at Idaho National Lab, we're anticipating to have power production in 2025 with further commercial projects in 2026 and beyond. The reason we're able to do this in this amount of time is because we're deploying a technology that's already pretty mature. And the US National Labs have done a ton of work to develop the technology that we've used. So our business plan was always to pursue technologies that are already in a mature state. Okay, this is a slide that's full of a lot of words. I covered some of the things that are up here. Just wanted to give a sense of, hey, we've done a lot more things than what I just covered. Additionally, in 2019, we became a company with Launch Alaska. We've been engaged in Alaska for a long time and are excited to be here. And to that point, this is our powerhouse that you see on the right. I know it was on the first slide as well. It's an A-frame, which of course is great for snow loads in places like Alaska. It also is a very small footprint, so we need less than an acre of land. You don't need any water, and this is what gets me really excited as the siting lead, is that we can really put this anywhere. And so it's a very robust facility. It does not need very many natural resources, which means we can focus on things like where the community would prefer it to be, on avoiding ecologically and culturally important locations, and that I think is extremely important about this design. More information about the actual design is that its electric capacity of 1.5 to 15 megawatts electric, which means it's 4 megawatts thermal to 40 megawatts thermal. It's metal fuel type with metallic fuel coolant, which means it has really great heat transfer properties. So as we all know, metals conduct heat very well, and so that helps with our inherent safety case. The capacity factor is greater than 90%, so that means that it's up and available basically all the time, and this is possible due to having refueling cycles of 10 to 20 plus years, so that means that we're not down for refueling. It also works very well with renewables. We can add energy storage to the system, and we can also produce heat or power or both. Okay, as I mentioned before, the experimental breeder reactor 2 was a reactor that operated at Idaho National Lab for 30 years. And we've talked a little bit about walk-away safe, and what's great about the reactor design we're using is that it's really proven walk-away safe. This is something that's operated not only in the United States, but around the world. There's commercial facilities around the world. This is a proven technology. It demonstrated inherent safety with a couple different tests. I'm happy to talk about those during the Q&A session. I know we don't have a lot of time during this presentation, but Oklo is really capitalizing on the proof of concept that has already been done by the national labs. Additionally, this is where we'll be getting our fuel. So our first fuel load will be coming from the experimental breeder reactor 2. So that shows that this is really very similar characteristics and design to reactors that, while very different from existing light water reactors, are very well proven. So some of the operating benefits of nuclear in general. Nuclear doesn't require that many materials. You can see here it's just very little compared to other power sources. So there's inherent cost benefits from just having less materials, as well as as compared to existing nuclear power plants today. There are just a lot fewer components. It's passively safe, it's very small, and it's a very simple design. So additionally, we use widely available materials for basically all structure systems and components. This can be readily shipped on existing roads using existing transportation methods. Okay, so just a little bit about the Oklo business model. So what we learned talking to people is that people do not want to own a nuclear power plant. They want to buy clean electricity that's affordable and reliable. So Oklo owns and operates the power plant and offers power purchase agreements like other power generation sources. We have, of course, for advanced nuclear to be successful and for Oklo to be successful, those terms have to be competitive with other power sources. And so we're offering these at competitive prices. Additionally, Oklo not only owns and operates, but decommissions the facility. Additionally, for Oklo, the fuel is a very important resource for us. So we take that back and use it so that we can use it in future reactors. If you want to learn more about us, definitely follow us on social media. There's lots of news stories out there about us. We're in time. And you can, on our social media, you can see some great interviews with me and some of the other people that work at Oklo. And thanks so much. Appreciate it.
Thanks, Emma. So again, please raise your hand if you think you have a question. We can get you a comment card, and then we're going to go into question and answer after Mike Floor. I guess with a V, I'm pretty sure that you're probably the last one here. I got that one right. Okay. Excellent. Okay, go ahead.
Thanks, Gwen. So hi, everybody. I'm Mike Floor. I'm the Senior Director for Advanced Reactors at Westinghouse Electric. I actually started my career working in several very old coal plants. So I've worked on the coal side, and now I've worked on the nuclear side for about 13 years. A little bit about Westinghouse. We are a 14,000 person company. Our company was actually just valuated yesterday, maybe the day before yesterday, at $8 billion. We have been serving the nuclear industry globally since the 1950s. There are more Westinghouse reactors in the Western world than any other technology that's been developed, and I'm very proud to say those are some of the safest operating plants in the entire nuclear fleet in the United States, substantially France, Korea. We've really been major champions of nuclear throughout its entire existence. We do everything from the fuel, the manufacture, the design, the manufacture of components, the servicing of those plants. Basically, Westinghouse has the capability to do everything for an entire nuclear plant. We're finishing 2 plants, full-size plants of our AP1000 design in Georgia at Plant Vogtle. Those will be the first new nuclear units online for a long time. We also have 4 of those units operating very successfully in China. But those are, this is kind of the history. We've worked a lot on these older plants. But really what we're here today to talk about is what Westinghouse is doing. Oh, this does go very fast. I should have noticed that. But what we're working on now is an advanced reactor that is a microreactor, which is very different from the very safe operating large nuclear power plants, as you've probably seen throughout some of the presentations today. Their physical size is much smaller. From a safety aspect, that has a major impact. The maximum credible accident simply from going much smaller is very different. As was touched on a little bit, the size of many of our microreactors we've been talking about, including Westinghouse's, is very similar, if not even the same, as research reactors that operate at campuses throughout the United States. Those research reactors are generally on campus. Some of them are actually located right next to campus housing. They are generally secured by campus police response, and they are generally operated by well-trained grad students. So there is a very analogous situation from a security, a safe operation. How do you really do this in the United States right now in many universities throughout the United States? So a little bit about the eVinci microreactor. So Westinghouse has been developing this technology very quietly for about 6 years now. And we started the development of this technology by actually sending a few people quietly to Alaska and Nunavut to really look at what we saw as the design requirements that you would really need to be able to successfully deploy a commercially competitive microreactor in the most remote and most difficult areas to construct. So we developed a transportable design that is capable of generating 5 megawatts of electricity, as well as capturing about 8 megawatts of thermal at 200 degrees C, or around 350, 375 degrees Fahrenheit. We can make both that power and heat in combined operation mode, minimum 8 years of refueling. So similarly, it's a much longer refueling cycle than the large plants today. A large plant today, you generally have to take offline every 18 months. You have to take it apart. You have to move the fuel. You have to take some of the fuel out. You have to put some new fuel in. These designs, much longer fuel life, much more predictability of the cost of electricity throughout a very significant period of time. This design, very transportable. When we looked at Alaska and also in Nunavut and other areas throughout the world, we saw that transportability does a lot of things. It also helps to solve the problem of spent fuel currently residing on the site of operation of all the existing nuclear power plants in the United States. So with this design, we actually, after it's operated, we remove the reactor with the fuel inside it in a qualified fuel transport cask, which Westinghouse moves Generation 2 plant fuel all over the world. And we do it using multimodal transportation. We have a fuel factory in Columbia, South Carolina. We have a fuel factory in Västerås in Sweden, and a fuel factory in the United Kingdom at a place called Springfields. And to tell you what can be done with moving fissile material safely across the world, Westinghouse actually has shipped our fuel from Västerås in Sweden to the Ukraine. So Westinghouse has been supplying Russian fuel to Ukraine, Russian designed, but displacing Russia from the Ukraine for about 4 or 5 years now. And we continue to do that. That's actually one of the most difficult transports of fuel. You have to go across the Baltic. You have to go through multiple countries. You have to use multiple modes of transportation. That can be done safely, even with existing plant designs. Certainly with safer fuel, it's actually even easier to accomplish. From a cost competitiveness perspective, as you'll see, the design of our reactor is extraordinarily simple. And we've done that because we felt it had to be very simple and very small to make it cost competitive when you're only getting an output of 5 megawatts of electricity per unit. And what we've been really proud of in Westinghouse is we've actually been building and testing components of this reactor for 6 years. So the heat pipes in our reactor, we have been building since about 2019. We've been testing them at full operational temperatures. We've been putting them in research reactors in the United States, all to make sure that the actual product can be built and delivered, because that's what's critical from a Westinghouse perspective. You know, the licensing is often talked about, you know, some of these upfront processes are often talked about, but you also have to be able to actually physically deliver these designs. Otherwise, you don't get that end benefit. And then from a load following perspective, these small reactors, mostly in general, can load follow much faster than nuclear plants that are generally base load. This is our design. I won't talk a ton about the design, but what is different of ours is there is not a pumped reactor coolant system. So when you talk about Fukushima, what happened at Fukushima, which is one of the well-known accidents in the entire world, what happened was they lost their diesel generators when the tsunami came, and the power output from that plant was also lost. So the plant had no way to continue water circulation through the fuel. And in the existing plants, if you cannot maintain water circulation, the fuel will get too hot, and that can cause an accident, which is what happened at Fukushima. Many of these designs have much advanced fuel, including the Vinci that uses a TRISO-based product, as it's been talked about today. But also, this design does not have any pumped reactor coolant system. We are using completely heat pipes for transfer of heat, which are very similar to thermosiphons, which operate on the Trans-Alaska Pipeline to keep permafrost frozen. So we're actually moving all that heat without any mechanical components. So by definition, your ability to maintain your cooling is much improved than if you have mechanical equipment that relies on electricity or other motive forces to actually keep your reactor safe. Also, this design, when it's operating at full power electricity, it has no moving parts, which from a reliability perspective, we actually see, you know, nuclear power plants, they're very large, very complex. Some of the nuclear plants on Earth right now achieve 92, 93% availability. And that's with a very large, complex plant. This literally has orders of magnitude lowers the numbers of components. Next slide. What I'd like to just highlight last, and I didn't go too slide heavy because I just wanted to, you know, have a conversation here. We are now in the pre-licensing process with the US NRC on this design. So we have been building and testing and building up our design and our information and our ability to then deluge the NRC with information, which they're maybe happy about, maybe not. But since December of last year now, we have submitted technical documentation on all these key areas, and I won't go through them all. But what's important here is these are many of the things that people have been talking about are necessary for these advanced reactors to come to the world. You have to have improvements in how many security resources you need, which we have, you know, our security plan has been submitted to the NRC. You know, you have to have a plan for how you're going to refuel and decommission. You have to have all these things. So Westinghouse has been building this technical volume up. We've sent it to NRC in the pre-licensing process. We've gotten formal feedback on 3 of the 4 tranches of papers that we have sent. The 4th was just sent recently, and our final will be sent on November 2022. So this will now position us very well to move into what we're doing right now, which is finalizing our design for a test reactor that will operate at Idaho National Lab, and then go for full US NRC design certification for this product. And this is a path that, you know, we had talked about quite a bit with the US NRC, and we felt was really the right approach to do something new. Is you have to do, we felt, a lot of physical building and testing to prove it. And so that's the body of knowledge we've been building up over the last 5 years. I'm really happy to present to you today. This is my, I think, 5th or 6th trip to Alaska, 3rd to Fairbanks, and I was very glad that my job could bring me to Alaska. Because I've always wanted to come here, and now I've had quite a bit of opportunity. So I really thank you for your time today.
Thanks a lot, Mike. Can you guys go ahead and make your way up here, please? So we're just going to go ahead and jump right into the Q&A again. If you have questions, Okay, trust me, I have like 35 questions here, so we're not going to run out. But I really want to hear from you guys in addition to my own. So I do want to mention, too, that we're going to be taking questions from the folks that are participating online via the live feed. And my co-moderator of the Alaska Working Group is helping to kind of collate those questions and get them to me. Her name is Rochelle Johnson. She's with the University of Alaska Anchorage. And I just kind of want to acknowledge her role in a lot of this and invite any of you that are interested to also participate in the working group. It's open to the public. It's a way that we share information and that we bring speakers in so that we can kind of continue this dialogue and continue to learn together about the technology. We often have vendors present. We've had the NRC present. I believe that the Air Force is going to be presenting in the near future as well. So really, if you Google it, you will find it, but I think you can scan. There's like things out here that you can scan too, little QR codes. So with that being said, thank you all for the presentation. Really appreciate it. I guess I'm going to get some cards, but before oh my gosh, really? Okay, well, I'm going to start with a couple of mine so that I can, so I can read through these a little bit here. But it looks like, we've got a lot of different size reactors here, right? So Emma, your reactor, the Oklo reactor, is a 1.5 megawatt reactor. Christian? To 15. To 15, but wouldn't that be like deployed in modules?
No, it can scale up. It would be that's a single.
That would be a single, okay. Thank you for explaining that, actually. And so Christian, you're talking 5 to 7 megawatts electric, 30 megawatts thermal. Oh gosh, yeah. I'm just repeating what I heard. So maybe. So
is it on?
Yeah, they're all on. So you guys shouldn't have to do anything there. So, and then the eVinci reactors, 5 megawatts electric output, roughly. I'm not right. And so then Josh, BWXT has several reactor designs of different sizes, including the really small one for the transportable. But that's also 5 megawatts or so.
1 to 5 megawatts on that one. So.
Okay. All right, great. And then Lisa, you're kind of looking at a different market with NuScale. So a single module is like 77 megawatts, and you're intending to deploy those in multiples of one. So you mentioned the 4-pack with like 300 megawatts is potentially being suitable for like a rail belt Alaska application or something like that in the future.
Right. That's the small reactor.
And that's like your small reactor.
Yeah.
Well, no, then you have that right. Okay, you're also working on a microreactor design.
1 to 10.
Yes. Okay. Awesome. So I'm curious, Mike, you kind of mentioned doing a little bit of market research. It seems to me that that these do fit different niche applications. I'm kind of curious, like, to what extent are your reactor designs sized based on sort of technical constraints, and to what extent are they based on sort of market drivers? I'm sort of curious about that, and like I don't want to spend too much time on one, but if any of you want to jump in and start with that, I open that to all of you. So, because I got some questions to read. So.
Yeah, I can start there. So from the eVinci perspective, we are 15 megawatts thermal, approximately 5 megawatts electric. It's actually 5.2, and also it's temperature dependent. Lower temperatures, we can actually generate more electricity, which is generally common. We looked at the market and the technology both. We felt that commercializing at 5 megawatts, we could achieve a commercially competitive product, even right out of the gate, really with the first reactors, especially in markets like Alaska and northern Canada. And with our design, our plan is actually to do a bit of the reverse of what many are doing, which are starting to go larger, is we actually see the ability to reach full-scale manufacturing, reduce the costs of producing the product over time, which has happened with basically every energy technology that has become common. And we actually plan to shrink the design further in the future, which could serve some of the areas of Alaska that certainly do not need and would not even be able to support a 5 megawatt electric load.
Well, I can add from USNC point of view. Well, as I said during my presentation, we start looking into the mining as a starting market. That was the initial design, and at the same time, it's a trade-off between you want to if the demand in one spot is 50 megawatt, to supply that demand with only one unit is actually a source of problems in terms of reliability. So you probably would like to have multiple units serving, 50 megawatts. So in that way, we don't really have a very large need for backup. And so that was the reason for looking to that size.
And then just to add from Oklo's perspective, the slide that I breezed through that had the timeline included some agreements that we already have in place for Bitcoin mining, but generally this size of our design is based on basically a Tesla model of how we're developing. So our very small reactor, 1.5 megawatt electric, is kind of the initial Tesla roadster that was, kind of a first starting place, and then we are moving and scaling up based on partially demand. We definitely have a lot of customers that we're working with, but also based on just we're being able to escalate up to have cheaper reactors that we can deploy everywhere.
Great, thank you. So this is a question from the audience here. And one thing I do want to distinguish between is the idea of a small reactor, like a microreactor, and an advanced reactor, right? So the question here is, how many operating microreactors are there? But really, I think what the question is, because we had a microreactor operating in Alaska, if you want to say that, right, at Fort Greely. So what I think the question is really referring to, are there any operating advanced microreactors in the US or anywhere else in the world today? That's a question. And then related to that, what about these universities that have these research reactors? Like, how many of those are out there? And how many universities have their own nuclear research departments? What's the advantage of having a reactor at a university? So if any of you that has knowledge of that could chime in.
I think that we represent different technology, right? So I can speak for my technology. The HTGR, high temperature gas reactor, they are currently operational. For example, there is one in Japan, it's prismatic like ours. The fuel that we use is special, but I would say that our technology is incremental with respect, already existing reactors. So maybe they are not micro, they are larger, but the point is that pretty much most of our technology is already tested in different type of deployment. Maybe not all together, maybe not micro, but it exists.
Anyone else?
So I think I'll shoot at the second question, which was the research reactors in the United States. I think there's somewhere between 12 and 20.
It's more than that.
Is it more than that?
Yeah.
Some of them only operate for like a week or so. It's hard to tell if they're active or not because they use them just solely for a couple of classes. Some operate all the time. Like if you go to the University of Missouri Research Reactor, they operate 52 weeks out of the year making medical isotopes. So you've got a lot of that in the industry. MIT's reactor operates and does a lot of testing of materials and capabilities that a lot of us are taking advantage of. And then you've got some universities that, Texas A&M, for instance, I think they operate theirs maybe 2 or 3 weeks out of a year just to teach a class. These are small reactors. Some of them are 250 kilowatts. Some of them are up to a megawatt. University of Missouri's is 10 megawatts. So those are throughout the United States. Nuclear engineering programs, Mike, do you know? It keeps growing, some 25 plus.
Yeah, I think there's probably over 50 now nuclear engineering programs at universities. Some of them are quite small, some of them are quite large. There's a couple of the programs put out 60, 70 undergrads per year. And there's because of this advanced reactor discussion, there's actually a huge amount of demand now for not just nuclear engineers, but also other mechanical engineers like myself that did some nuclear classes in college, but I'm not a nuclear engineer. And also just from the research reactors, they're not just used for the testing of material. They certainly are. They're not only just used for isotopes. It's actually amazing some of the things that they do. At Penn State's research reactor, Westinghouse is doing a project there with eVinci to actually bring them another. eVinci has another research reactor. They're going to keep their existing one. They actually do irradiation of seeds and different things to study. They do creation of different isotopes, not all for medical, but then they also do things that you really just need neutrons for. That gets pretty complicated, but imaging and doing things like a scanning electron microscope type of approach. There's things like that you can do with a research reactor. There's just a huge amount of things, and then they also serve a purpose of being somewhat of a test bed to be able to try new systems and components. So the Penn State Research Reactor has operated since like 1955, and it's actually not the same reactor anymore, because over time they've just tested new improvements, new changes. It's a completely different reactor now in 2022 than it was when it first operated. So they also help us innovate by being able to try things in an environment that's very accepting of it, and it's a very safe situation.
And then adding on to that, thank you for that. Adding on to that for metal fast reactors, which is the type of reactor that we're developing, those have been operated all over the world. There's multiple fueled fast reactors that have been operated in the United States, the fast flux test reactor, and then the experimental breeder reactor 2. There's been over 400 operating years of this type of facility around the world, so this is not really a new thing, and it's demonstrated some pretty amazing things. So, I mean, Mike talked about Fukushima and about like loss of power there and how it was, that was the problem. This has actually been demonstrated in EBR2. They shut off the pumps. They went to lunch, so literally walk away safe. And there was no problems. And so, that kind of operating experience is something that is really great to have as we continue to develop.
Yeah, I think I actually was going to ask this question, but you essentially just answered it, Emma, because it was directed to Oklo. So, the question is about this R&D needed for use of coolants such as liquid metals and molten salts, and I think that the answer is really that this is not as new as we might think it is, because it sounds very new, right? It's from a lay perspective.
Yeah, I've always disliked the term advanced reactor because it's like, okay, this stuff's been around since the 1950s. Like, it's not as new as advanced implies.
Mm-hmm.
I'd just like to make a comment on that NuScale is actually using some combinations of fuel and coolant that maybe haven't been deployed in larger reactors before. So while we're still in this early conceptual design phase, we're working with a lot of universities to scope testing to make sure that the properties of the fuel, the properties of the coolant match what we are modeling and the type of activity, the type of reactivity we think we can get out of the combination. And we're doing a lot of early characterization to really understand our system before we go too far into the development and building, and before we start our licensing application with the NRC.
Thank you. So I'm going to combine 3 questions here that are really all around this walk away safe. So one is from the former director of the Northern Alaska Environmental Center, who asks that question, like, please be a little more descriptive what walk away safe actually means. But to kind of like add to that, there's a lot of questions about like specifically what would be the extent of damage or plumbing, damage from a catastrophic kind of earthquake or something like that. I mean, obviously Alaska has pretty extreme events like this. And then kind of related to that, and I think this is actually an interesting question I haven't seen before. So fine, safe to walk away, right? But like we're sort of seeing potentially to some extent in the Ukraine right now, what happens if that electric distribution or transmission to load is damaged over some long period of time because of some sort of a natural disaster or some sort of, an event which eliminates the need for electricity? Like, does it safely shut down and stay safe? What could get damaged? Like, what does turning things back on look like after some sort of an event or, issue sort of is over? So it's kind of a long question, but.
I'll take the seismic. So, from an NRC licensing perspective, seismic is quite well characterized across, the world and the different accelerations maximum that could be achieved at different locations. Alaska, basically, we all have looked at, analyzed for the seismic response that a reactor could see here. And one of the things to consider also for an advanced reactor or these microreactors is the small size actually makes seismic a much easier problem because it's a much more compact, dense device. Our AP1000s in Georgia are, I think, 186 feet tall at their maximum point, which we also have to design. Georgia's not a high seismic area, but we still have to design for the seismic loads. We have to show analysis to the NRC to show that we can deal with that. And you can do that even for a very large structure. So even then in a seismically challenged area, a much smaller structure it becomes quite achievable. And certainly we would not be able to license and deploy any reactor into Alaska that the vendor would not be able to show would be able to survive an earthquake event in the site of location. And there have been earthquakes that have impacted plants, and basically there's a process for shutdown, inspection, evaluation before then you restart. Yet it's a very well-known, characterized design process to design for seismic in nuclear.
I'll try to address the question, what is the meaning of intrinsically safe, walk-away safe? So for our technology, we rely on the physics. So our reactor operates at a certain temperature. And when you move away, you increase that temperature, the reactor suffocates. It's like you're taking away the oxygen. So what happens is that if you stop cooling the reactor will stop producing power. That's what exactly happens. So the reactor will stay at that temperature. So that's the concept, and that's what you use to say that the reactor is walk-away safe. So if you stop cooling, if you stop doing, operating the reactor will never exceed the temperature at which it's operating. And at that level of power, it's capable to dissipate the heat outside. So that is the property of the physics of the technology.
Yeah. I agree with that. Just wanted to add on that, like with, it's very similar with our design in terms of the inherent physics make it walk away safe. I don't use that term that much, honestly. But it's something where basically this is all metal. When metal heats up, it expands, and that stops the chain reaction. And there's not a lot of heat in these. They're very small, and so you can dissipate that heat. Yeah, and that's been shown with experimental breeder reactor too.
I'll just mention from the SMR side, I don't know if anybody noticed, I know I talk fast when I present, but there was a picture of all of the modular reactors kind of buried in a very large pool. So the pool is used for two purposes. It's seismic considerations, but also for to allow it to be walkaway safe. So if we didn't have control of the reactor anymore and people had to walk away, the heat in the reactor would dissipate into, there's heat exchangers on the outside of the reactor to allow heat to be exchanged into that massive, massive pool. Eventually the pool would kind of deplete, but we've done analysis that shows once it gets to a low enough level, the reactor continues to cool just by air cooling. So that's what we say when we mean walkaway safe for the SMR, is that indefinitely it can stay there until it's cool enough for, whatever, depending on what the accident was or what the, if there were any breaches in the reactor container or what, cool enough for it to be approached again or mitigated.
So Josh, I'm gonna ask you the next question. So unless you have like a burning response.
They did a very good job of covering it, and we have very similar technologies across a lot of our reactors here. So.
Right.
Yep.
So I know WXT does a lot in terms of fabricating fuel, and so that's why I wanted to ask this of you. Could nuclear fuel for small reactors be processed from decommissioned nuclear weapons?
That's a loaded question. So in my career, I've worked on 4 programs to use actually plutonium either from spent fuel or from nuclear weapons back in light water reactors. The Department of Energy funds that. It goes for about 3 years and then it goes away. The technology is there to do that. The economics usually don't prove themselves out at this point. it's one of those things that if it was there, the once through fuel cycle, mining uranium, enriching it, using it in the reactor, storing the waste safely is always a viable solution at this time. The technology remains that we can reprocess it. France does that today. They do that, and believe it or not, that's actually U.S. technology that France uses to reprocess their uranium. It came out of the Department of Energy. It's just something we as a nation are going to have to decide. There's a lot of energy that remains in spent nuclear fuel or in other plutonium sources. I mean, light water reactor fuel, you know, you burn 3 or 4% of the energy out of there, and you still have 90+% there. That's a resource. You know, even back in the 50s, some of the great minds who set up nuclear power and the clean said, whoever sits on the remaining nuclear fuel is sitting on a gold mine. And there's more than just the energy in there. We talk about medical isotopes and other things that you can get out of there that would provide a benefit to society. The technology's there. It's not an easy process. It's very labor intensive, very cost intensive. But at some point, we might choose to do that or not. So
I've asked Ben Beasley from the NRC to join us because I'm realizing some of these questions are also directed at NRC, and I think, Ben, you wanted to comment on this as well.
Yes, so I agree, Joss, that technology is there, but the non-proliferation treaties prevent us from using weapons fuel for commercial uses. And so the answer is just a plain no, we can't do that because of the international treaties.
It might also be helpful. I don't think any of us said it. So the enrichment level of the uranium that all of us are using is below 20%, and weapons grade uranium is over 90% enriched by definition. So no commercial vendor is looking at exceeding even that 20% threshold.
So would you, just to clarify that, just to make it crystal clear, so basically the types of fuels that you're using in these reactor designs don't have the possibility of exploding, right? They're not designed for all those fissile reactions to happen at once like you would see in a nuclear weapon. Is that an accurate statement?
Yes. So that enrichment level of 20, you would not be able to, you couldn't use it in weapons, but there's other things you would have to do even if you had 90% enriched uranium to actually create a weapon reaction.
Okay, thank you.
You know, high enriched uranium, for instance, also, because we talked about, has been used in research reactors in the United States, actually a significant amount throughout the history, and still is. So it is also not something even at a high enriched level that is impossible to do or be handled even by a non-military entity.
Thank you. So Ben, I said that there's some questions here for the NRC, so I'm going to ask you this next one. And I feel like this has been discussed a little bit, but it'd be great to get a little clarification here. When do you anticipate that the NRC will have updated regulations in place to consider approving an advanced microreactor?
So we don't need to establish any new regulations. The current regulations can be used for an advanced design, although we are working on a new regulatory framework that will make the licensing process a little bit smoother. But we are currently reviewing an advanced design with the existing regulations, and there are some adjustments that we need to make with respect to, you know, some of the regulations don't apply. Some of the regulations are inherently met, and so we don't need to review against them, but we currently are able to review some of these advanced designs with our current structure.
Thank you. So we've got some economic questions. So, you know, I think folks are really interested. You guys have talked a lot about being price competitive with conventional technologies. There's still a lot of unknowns, right, associated with deploying these reactors. You know, do you guys have an idea of like the sorts of price targets that you're looking at achieving, or anything that you'd be willing to share related to the economics of these deployments?
Yeah. So we did the public-facing document that we have done was a feasibility study in Canada, actually, but it's very similar market, very similar from a cost structure and we did this looking at a mine site And we came up, and this is about a year ago, so there has been some inflation, but actually the inflation costs in nuclear have actually been less than most of the fuels we're competing against. So we came up for eventually that we could produce even a very early, if not the first reactor, at about 25 cents a kilowatt hour. So again, that was about a year ago. There's been some inflation in that, just in metals and other things. And what we see is when you reach, where we're basically building these like F-150s at an assembly plant, we can achieve really, sub 20 in the teens type numbers. And then for the recent Inflation Reduction Act that was just passed, there is now production and investment tax credits that apply to advanced nuclear and other forms of nuclear, actually, or existing nuclear. Investment tax credits can have a very large reduction in cost per kilowatt hour, even on top of that. So it's one of the reasons why I think probably all of us are quite excited about this technology is you can see a path where it can be competitive in most markets. And now in Europe, I will just note the wholesale cost of electricity throughout mainland Europe now is over 50 cents a kilowatt hour. So when you think about the cost hurdles that have to be achieved, it's actually getting easier for us to compete in a lot of places throughout the world. And I would have never guessed that wholesale electricity would ever exceed 30 cents a kilowatt hour in a lot of places in Europe just a year ago.
So I've got 3 questions here related, and I'm going to read one of them. They're all really similar. And this is about truly remote small villages in Canada or in Alaska. So talking about a community of maybe 200 to 500 residents. And so I like the way this one is structured. So who among you believes that your business, growing as it is now, could sell Alaskan communities like, in this case, they mentioned Anaktuvik Pass. I'd say maybe Galena with 500. Anaktuvik Pass has, maybe 200 residents. A leave alone, basically a nuclear battery, by 2050. And I kind of like that further out date. Like, how realistic do you think that by 2050 we could eliminate the need for diesel generators in many rural places and replace them with very tiny nuclear batteries, which may be quite different than what you're working on today? I'm just curious, which one of you think that that's feasible or not? Who wants to? I can just go. We should start with Ben.
So yeah, I'm sorry, I can't speculate on that. My job is to make sure that whatever they build is going to be safe. And beyond that,
Excellent. Awesome.
I mean, I definitely think it's technically feasible, and if there's a demand and there's customers that are really interested in that, Oklo is looking to engage with people and different customers. That is not the reactor for that low of power demand. That is not the designs we currently have. So that it would have to be a different design.
Similar answer, just the fact that we, as a company, we are also looking to space application with reactors that are much smaller for, Moon or Mars, and also for, nuclear thermal propulsion. So probably this type of design, they're more suitable for these remote communities. So, yes.
Mike, what do you think?
Me?
Yeah.
Yeah, similar. I didn't pipe in. Christian said it. I mean, we also have an award from DOE and NASA for a very small reactor, where weight and size is ultra critical for delivery to space. And I think what it will take, and I mentioned we're starting out at 5, and we actually plan we can shrink the reactor. Is as you get good at making all these components, deploying as we develop and work with the NRC to make the licensing process perhaps a bit more cost effective and other things, but also a lot of that's on us to prove our designs are safe. You can foresee a potential path. I mean, 2050 is a good number because it might be right on the border of when you think you could do that or not, but it's physically, I agree with, it's physically possible. It's a question of whether we could get the cost of a reactor at 500 or less kilowatts at a point that would be economically viable.
Yeah. Okay. So, I mean, I think what I'm hearing, and I'm probably going to hear from Josh or Lisa too, is that it's technically possible. It just might not be cost competitive. Is that fair?
Yeah, I think we'd say the same thing.
Yeah.
We're working on the lunar power solution as well, and you're talking kilowatts there instead of megawatts. But you're also still talking about space constrained, weight constrained systems, and when you start to shrink them into those sizes and put them into fairings that go on top of rockets, that adds a lot of cost actually in and of itself. You think making it smaller makes it cheaper, but when you start to constrain it, it makes it more expensive. So it would be a balance in there, and you'd have to look at, are you doing it for one community, or is there 50 communities? In which case, then maybe there's a chance to invest in the design, get the cost down, and make it implementable.
So I guess you brought up space reactors just now, and so I mean that's a pretty, once that guy's out in space, like there's not going to be any workforce working on that reactor. That's truly a hands-off type of reactor design, right? And so question that we have here is for these terrestrial applications, what are the workforce requirements going to be? What should we expect, like for your reactor design? And I realize that there's still some open questions about that, but what would you anticipate, and what types of skills would be required? And I'd actually like to ask not just for the reactor, but also for the power conversion equipment, so the generation equipment that would be connected if you're planning to produce electric power. Do you guys want to take a stab at that?
Just to start off, in terms of our on-site monitors, the only requirement there is that you have a high school diploma or equivalent, and so that's the technical background. In terms of construction, it's a construction site, and so it's going to be electric workers. It's going to be people working on pipe fitters. It's going to be people who do construction projects for construction there.
How about for operation?
Oh, for operation, as I noted, for on-site monitors, it's just having like a high school diploma or the equivalent.
Okay, thanks.
Operations staff are going to be set with NRC during your licensing process. That's something each of us are going to have to go through. You also have to have support services around nuclear reactor, fire, health, safety protection, sometimes, and security requirements, which are also going to be set by the U.S. NRC. So each reactor is going to have some requirement in there. That being said, I will state that there is this synergy between space reactors, which kind of drove your original question, and back to terrestrial reactors, is that we are going to operate these space reactors with no humans, remotely from Earth. That brings a technology that enables us to say, okay, I can bring this technology to bear. I go to the US NRC and I make the case that I can reduce the number of staff that I need at a reactor. Are we ever going to get on the terrestrial reactor to zero? I don't think any of us up here will say that, and I know Ben definitely won't say that. I don't think that's ever our goal, but it's our goal to try to make it as cost effective in the staffing and safe as possible that we can do that.
I've got a lot of questions here about fuel. There's always a lot of questions about fuel. So in this case, it's really about what you're going to do with spent fuel. How much is expected to be produced, and where would be the final resting place for the Eielson, both high and low level nuclear waste?
This is a question that we at Oklo always like, because spent fuel is an asset to us. It's been proven that with this type of a reactor, a metal fueled fast reactor, that you can recycle what's currently considered nuclear waste into fuel that we can use in that facility. And this isn't something that's just theory; it's something that was shown at EBR2. So for us, the fuel is an asset that we want to take back. We want to take with us back to use in a future reactor design. And it's basically because of the neutron spectrum. It's a fast reactor, which means that there's a different ability to use different isotopes that are in existing spent fuel or used fuel.
So for the SMR, the current plan is similar to existing nuclear plants, where when the fuel is removed, it is stored. It's going to be stored in these big deep pools until it's cool enough to be packaged into dry casks that are I'm not sure the right term, approved by the NRC for long-term storage. Once they're in dry casks, they'll be stored on site, similar to the nuclear waste is stored currently. For the microreactor, we plan to have a similar model to what some of my colleagues talked about, where you would basically remove the entire core, so all the fuel that's in there, it would be refueled every 10 years, so it would need to be cooled down to the point that the whole core could be removed and replaced. As far as long-term storage of that fuel, shorter-term storage could be done on site. Long-term storage, I think, is more of an industry question than just an individual vendor's question. I know there's a lot of policy work that's being discussed on a site and budget allocated to establish a long-term storage facility, but I don't think that it's there yet.
And I'll just speak to that slightly because I don't know much about it, but it is the responsibility of the federal government to take the spent fuel.
Right. So in our case, there will be not need to go in a pool, but it will be just going straight to dry cask. Probably some cooling time. What we like about our fuel is that it's very robust. So if you separate the fuel from the moderator, the graphite, you actually end up with a very low amount of waste that needs to be disposed.
So I do want to actually distinguish, because it's interesting what Emma was talking about with the potential for recycling fuel. So just to be clear, you are not all using the same type of fuel for your reactor design. And so, in the last town hall, we talked a lot about this TRISO fuel that was mentioned by a couple of folks. The eVinci reactor is using that. I think the Pele reactor is going to use TRISO fuel. BWXT is manufacturing TRISO fuel. That's that encapsulated fuel. Now that is going to be, as I understand it, fairly hard to recycle. I mean, we have to be honest about that. The benefit of it, which is that you're encapsulating that fuel, also is going to work against you if you're trying to actually recycle that fuel versus like a liquid metal fuel. Is that fair?
No, that's a very true statement. So, I mean, even when you make TRISO fuel, sometimes you want to recover it because it's not on spec. That's hard enough to break back into when it's clean to go and recycle the uranium, put it back in the process and get it in to make sure that it meets the specification. It's very hard to crack and everything else, so it's not meant to release the stuff that's in the center. So you could recycle it. The technology is there, but it's not going to be cost effective as compared to somebody who does have a metal fueled reactor.
So we're going to have to wind down. Like, this is really fantastic. I've actually gotten through a lot of the questions, which is great. A couple questions related to cost again, but a little different angle here. One is there a significant a cost reduction post refueling? So once you refuel the reactor, so maybe some of those like capital costs can be paid down. And related to that, we've talked about the potential for sort of load following or really being able to not just run these at base load power as conventional reactors mostly have been used in part of the U.S. fleet. And so, like, for example, Christian, when we talk about Valdez, where it's on hydro part of the year, right. There's this possibility of having a reactor there that could help offset diesel in the winter, but maybe you shut it down for part of the year. So, this kind of goes back to there's the technical feasibility and there's the economics of actually operating in that way. So I guess that's a little bit of a two-part question. Number one, like, once you refuel this reactor after whatever period of time that is, do the costs go down? And number two, how you're operating it, like, does that fuel just last longer so it doesn't really matter? Or is there like kind of an economic hit if you're not operating it at sort of more a base load output?
I guess
Go ahead.
I'll start, right? So, yes, you said two parts of the question. First part about what happens, when you do the refueling, if after that it is less expensive. Well, it's really like a mortgage on the house in some sense, right? Depends how long it is mortgage. And current licensing from NRC, 40 years, right? So, the plants that we have today in the US, they've been extending to 60, 80s. So the loan that you may decide to take maybe lasts only 20 years. After that, the capital is repaid. If you do the refueling, you have just to cover the cost of the fuel, right? So that definitely drives down the cost. With respect to the question, does you get negative impact from not using the reactor 24/7 or 24/365? Some, not as much as the current light water reactor, and the reason is that if you burn slower, it's going to last longer. So essentially, what is going to happen is that you will be able to use your fuel later on. That helps preventing economic disadvantage from the operation, for low operational factors in the plant. Of course, you will not send people home, so the people will still need to be paid even if you're not running the reactor for the whole day, right? So there is some sort of trade-off, but this type of technology where we can stretch the lifetime of the cores will mitigate the cost generated by low capacity factors.
Anyone else? Yeah? Okay. We're maybe kind of coming down to the last few questions here. I am curious if any of you could comment on the status of nuclear fusion or thorium reactors. There's got questions on those too. Why are we not using thorium, and what about nuclear fusion? Anyone want to comment on that?
I'll be brave and I'll go first so I get to choose which one I talk about. So fusion has been that technology that's always been, and you can pick your number of years, it's either 20, 25, 30, 50, 100 years away, no matter how many years go by, right? There are now many companies working in that area to try to commercialize fusion technology. There's been a lot of work done at the national labs where there's been some promising results, but those results have not generally been repeatable, which usually signals there's still a lot of things you don't know. But there are now, one of the big fusion reactors that's being built is actually in France. It's called ITER. It's a very large design. It's much larger than it has ever been done. So they are really trying to achieve, instead of kind of taking this very slow approach, they're trying to achieve real fusion power in France with a global project, which Westinghouse actually manufactured some components for them. There are some companies in the US now that are taking a similar approach. There's 3 or 4 ways that people are trying to achieve fusion reaction, but it's not been done at a level that is repeatable or in most cases actually energy positive. So there's a lot of work to be done, but I'd say it's an interesting thing to really follow because at any moment maybe someone can start to solve some of these problems, but there's also a reason why it's been 20, 30, 40, 50 years away, basically forever. So until you get some repeatability and things like that, it's a challenge. There's also a challenge with the fuel. So fusion reactors will often say that you just need salt water, you just need water, because you can get deuterium out of water, but that's only one of the 2 ingredients that you need for fusion fuel. You actually need tritium as well, which is much less common, globally. So there are major challenges there, but there's also now this renewed interest. The US DOE is really working on funding this to really support, will some of these companies' technologies make it? Which is really interesting. I'm a fission guy, but it's interesting to follow.
And tritium is really just an isotope of helium.
Hydrogen.
Is that fair?
Hydrogen.
Hydrogen.
I think it's H3.
H3, yes.
Thank you.
Deuterium is H2.
Okay,
so.
thank you.
So from a regulatory standpoint, there is a huge a group of fusion energy companies that have formed an association and have approached us about starting to develop a regulatory framework for them. And so it would be completely different technology from the fission reactors. And so, we do need to establish how we would license those in theory, because it is a fusion reactor, there could be it's not going to, we do need to still license it, but it could be, in essence, not require a license from us because there's not, radioactive materials that they're going to be using. But if they operated a fusion plant for a while, then they're going to activate some of the containment materials, and so they would have some radioactive waste. But from a standpoint of what we typically look at, there may not be much for us to review. So that's, there is some development going on there, but as Mike said, it is several years away at best.
Thank you. Okay. I've got 3 questions left, and I actually want to try to get through them, and because then we got through all the questions, which is kind of cool. So I'll start with this is kind of like they're good questions, but they're a little diverse. So I'll start with a kind of an easier one, maybe. So how is the material how would the nuclear material be transported, the fuel, the fueled reactor, to the interior? Like, what would the process be for delivering it?
So physical process is probably you're going to have to go to the west coast of the United States, barge it up, and then you would have to some combination of rail, truck. It's a possibility that you can fly things in. I mean, I flew nuclear fuel way back in the 1990s.
Would you say there's a lot more nuclear fuel being transported in this country than we're really aware of?
Oh, yes. I worked in the nuclear fuel business for 18 years, so I've shipped hundreds of tons of nuclear fuel across the United States safely. There are shipping containers that are licensed by the NRC. They're under a certain process that they're built and manufactured and quality assured to contain the material, both fresh material, which is unirradiated, as well as spent material. And you'll see the spent materials are much, much bigger. And even the fresh materials are still pretty hefty cask, major lifts to get those onto trucks and things like that. So it can be done. Everybody's going to have to get a license for a container to ship their fuel or their fueled reactor in a safe configuration. And it goes through a process, and it goes through all the accident scenarios that you can imagine in terms of transport of, it runs off the road, it falls off a bridge, it gets hit by a train. It's got to survive all that. We used to joke, punch it, kick it, throw it, drop it, burn it, just about everything. There's some fun videos you can go watch about testing shipping containers. I'm an engineer. I love to geek out on that. Mythbusters, failure's always an option. That's what it seems like you do with a shipping container.
So basically, Ben and Ken they're the guys.
Yes, and then the test engineers get to have fun. So.
Okay, fair enough. Okay, I got this question from the legislature when we were working on SB 177 this year, and given what you were just talking about with punch it, drop it, kick it, and also the fact that we're talking about a reactor at Eielson Air Force Base. The question is, what would happen if a missile hit your reactor? What would happen?
I'll take it. So the easy answer that I'll go a little past it is, it depends on the missile, number one.
Let's assume it's not a nuclear warhead.
So we design for reactors, and maybe I'll punt this over to the NRC as well, but there are design basis threats that are constantly evolving that reactors and the structures that surround and protect them are designed for. One notable, which Westinghouse experienced as we were building the AP1000s in the Southeast, was the implementation of a change to aircraft impact. So the design basis threats, and Westinghouse actually does a lot of analysis on this. We actually feed information back to the industry and others on this. We actually have a team that is ex-military that focuses on the design basis threats that are credible to attack not just a microreactor, but also our existing large nuclear power plant fleet. And what I could say is the design basis threats are not something that will ever be public information, which I know is maybe a little bit unsatisfying, but you could also imagine why the design basis threats are not public, because then people would have a bit of, well, what are these things designed for? But that process is well understood, designed for all the different types of threats, which includes not just projectiles, but also if someone would drive a truck up to near the facility with an explosive, there are all sorts of things like that that are taken into consideration for security and safe operation. But I don't know if maybe NRC could speak a little bit to that.
I'm not familiar with this area. All I'm just endorsing the aircraft impact analysis is modeled after the 9/11 attacks, where you have a large jetliner that crashes into the reactor, and the ensuing very hot fire is a requirement. But beyond that and the knowledge on the design basis threats, I'm not familiar with that.
One comment that I may add is that I think that all the vendors, they have their strategy to address this kind of issue threats. From our side, we decided to build the reactor underground. That is one of the reasons.
Yeah,
Go
same.
ahead. Yeah.
Same. we're embedded.
All right. So Mike, I think this question is more generally applicable, but people seem to have picked up on you talking about no moving parts, and so the question is, in a reactor with no moving parts, does that impact efficiency? And then a related question was, are they quiet? Are they quiet? Like, do they make any noise? I haven't really been asked that question before, so.
Yeah, so we have moving parts if we're changing a load, but it's only a set of drums that rotate very small increments. So if we're changing loads, starting up, shutting down, that we're moving just one set of these drums that go around the core, they rotate slightly. But if we're sitting at a constant or near constant power level, that's where there's no moving parts in the reactor. So from an efficiency perspective, it actually helps us with efficiency because we don't have the house loads, as they're generally called, which are kind of the loads that are required to support the plant. So if you have pumps and other things, you're actually creating electricity out of your power conversion, but you're also sucking some of that back to operate your pumps or valves or other components. So we see a big efficiency advantage from the lack of those mechanical components. From a noise perspective, our reactor will be very quiet because of that lack of pumps and other vibrating components that would create noise. But we still do have the power conversion system, which will create noise. But we can silence that, similar to diesel generator silencers. There's a lot of things we could do to reach whatever decibel level would be required in a locality, a region, a state, et cetera.
And yeah, I also talked about no moving parts for a microreactor. So we similarly, if for the largest size reactor, if there was a Brayton unit incorporated for power conversion, that's got some spinning parts, so that presumably would make noise. But the reactor operating on its own, there are no moving parts. So I'm not sure if you could hear fluid naturally circulating. I feel like
So you're differentiating between the reactor and a power conversion equipment.
Right.
And since you brought up a Brayton cycle, you are looking at different kinds of power conversion technology because you've got the Rankine cycle.
Yep. And we're also looking at, for our smaller units, thermal photovoltaic cells for power conversion. So heat pipes transferring to basically to these cells for direct DC power conversion that would then need to be converted for use. And I'll just give a note. This isn't our reactor, but I went to Oregon State, which has a research reactor. It's called a TRIGA reactor, and it's so safe that you can stand like right above it. So I got to see it, the blue glow, and it barely made any noise standing right on top of the reactor.
Cherenkov radiation, is that what it's called? Yeah, that's pretty cool.
Yeah, so.
Just like my little factoid that I learned at Idaho National Lab is that's really from, what is it, like from electrons exceeding the speed of light? Is that correct?
That they're in.
In water.
In the medium that they're in, yes.
Yeah. So, okay, that's it, you guys. I thank you so much, everybody. I really hope, I really appreciate the respectful dialogue. Thank you to all of our panelists. Thanks to to Ben for pinch hitting at the last minute here. I really appreciate it. And we do hope to hold another one of these, potentially with the Air Force about the Eielson project. We'll see. But thank you, everybody. Really appreciate your time. So, yeah.
Thank you.
Cool.